Okay, so I'll start with the agenda. I'll start with explaining what memory window is, reminding everyone the good old memory window from IB Herbs. What is the motivation of extending the memory window? The proposed solution and some examples of address patterns. I'll continue with the API proposal and examples how we use the API, and I'll finalize with a summary. Okay, so what is the memory window? Basically, it's a way to expose an aperture of a pre-registered region. So as we see here in the illustration, there is a big chunk of memory regions, a pre-registered memory region. And it can be registered without remote memory access. And using a memory window, we can basically expose a portion of it with a remote access permission. It basically opens a window to that region, and it doesn't require any extra resources for the network transaction. And it's not a privileged operation. It's fast, it's efficient. You do it through by posting a work request, essentially. With memory windows, basically applications can have a much more flexible control on its memory. It can grant and revoke remote memory access. It can basically allow a remote access per transaction. It can also allow different different remote access rights to the same memory region using different memory windows per peer. The operations of associating a memory window with a memory region is called a binding operation. And also it's possible to overlap with multiple memory windows on the same overlapping regions. The actions that are supported are basically allocating the memory window, querying it, binding. The spec defines two types of binds, type 1 and 2. The main difference between them is that type 2 is associated with a queued pair. So you can use this memory window on a specific queue pair only in type 2. And the last one is to deallocate the memory window. So what would be the motivation for extending a memory window? So we see many use cases where the memory layout, the pattern of the memory that describes the memory that we would like to use for I/O, being laid out in the memory in different patterns. We've brought up here three main applications that we see that has interesting patterns. For HPC, we have this example of the Brook all-to-all algorithm. We can see it over here on the left, where on the aggregation stage of the Brook algorithm, there's a vertex that receives information from multiple nodes, and it should be doing the aggregation in this manner where one vector from one node in blue and the other vector from other node in red should be laid out in this fashion, and then with the third node in green also interleaved in this fashion. So we would like to perform such an operation with zero copy if possible. On the right, we see an example from vector graphics. Also, a use case where we have three vectors, and there's a stage where those vectors should be laid out in interleaved fashion in memory. Another one is from the scientific range. We'll see that in the next slide. So again, I'll reiterate the motivation. We would like to have a compact way, a reusable memory layout description where we can describe such patterns. and basically allow the device to be familiar with a specific layout and keep changing the address for different objects. So the example here, if I continue with the HPC case, is a simple example of a matrix multiplication operation where you are doing it in a distributed fashion. So you take one row and one column from each one of the matrices, sent to a different node, and each node performs such a calculation. Sending the line from matrix A is trivial, but sending the line from matrix B is more complex, because typical memory layout for such a matrix would be that the first element here will be at offset 0, but the second element of that column would be at offset n, where n is basically a line in the matrix. How we deal with it today? So two main ways to deal with it. One is to perform, to register a large scatter-gather list. Each such object is, as written here, is specified by its start address and the length. We have an array of these, array of scatter-gather elements, and we use them for sending and receiving over the network. Obviously, it's not the most efficient way to do it. The caching effect of jumping so far between those scattered elements is not efficient. In addition, building those huge scatter-gather lists is also inefficient. The other way to deal with it is basically to not to do zero copy. Just pack, so you copy the elements as described here to one contiguous temporary buffer and use that intermediate buffer for the network transaction. So what would be the proposed solution? Have the device be familiar with your object memory layout. So each transaction can use this layout. It would be something like a stencil. So you pass only a pointer, a length, and use that for the network transaction. And the device already familiar with the layout, so it can grab the scattered elements on its own. For send operation, obviously the device will do a local DMA read. Will be familiar with the layout, so it will do the DMA read from different location by itself and send on the wire. And also on the receive side, the device will do a local DMA write and will scatter the memory according to the predefined layout. Same thing for RDMA read and write. Once the device is familiar with the layout, it can read and write also from remote memory in that manner. The address patterns that we would like to define for such a layout, now that we need to define how we propose an MPI for that device layout awareness, we've seen two main types of such patterns. One is the composite. The composite is taking elements from, like a scatter-gather list, elements from different locations and binding them to a contiguous memory. So essentially, a virtually non-contiguous memory can look like a contiguous memory to the device. The other and more complex method is the strided data, which fits well with the column of the matrix, where you have a pattern which is repeatable. So in such a pattern, we would like to have a structure where we define how this pattern looks, and the device can combine multiple elements, and it can be many elements on its own. Another type is the interleaved data, where there are several memory locations that we would like to merge into a contiguous one. And the merge operation can be in different fashion. In this example, we see here that those elements are combined in an interleaved manner. Okay, now continuing with the API proposal and how basically we suggest to expose this through verbs. We see a good match with describing the non-contiguous memory with the already existing memory window verb object, and we suggest to expand that object to support such patterns. So the way we suggest to do it is that we extend the alloc memory window. In this slide, we basically see a suggestion how to extend and define a new alloc memory window EX using the already existing verbs extension scheme. So the verbs already have a scheme how to be extended, and we here suggest to use that scheme. So we have today the alloc memory window, and we suggest to use alloc memory window EX extended. Such a method would get the memory window, the new memory window utter that is described here. The interesting parameters that we pass here, which are new, the protection domain and the type were already in the legacy alloc memory window. The new attribute is the max descriptors, which is a hint to the device how much, how many different memory areas would be included in that memory window. So the device can be aware how much memory to allocate to a context if it uses a context for that memory window. The next one is the memory window itself. So today, the object, the handler that describes the memory window is the IBV memory window. The way to extend it through the verbs extension scheme is to define a new object, which is called a verbs memory window. It includes the old one, but also includes the new parameters. In this case, we have the descriptor number, the same that I mentioned earlier, but also the L key, since so far the existing memory window only supported an R key, a remote access. Also a structure that describes the capabilities. So we suggest to add that structure to the query device, which returns the IBV device utter structure. So we suggest to add to that structure the IBV memory window capabilities. Also to include information about how many underlying memory areas and keys can be supported in such an indirection memory registration. Jumping ahead and going to the main function, the main function would be the bind, and the bind today includes this is the memory window bind info. It includes today these parameters that are written in this nameless structure, the memory region that is being used, the address and the length that's the actual window that we would like to open from the memory region. So we take all that, we wrap it in a nameless structure, and with the union, we either use that those legacy parameters, or we have a pointer to a new bind layout. And using the access flag, we can define if this is a bind operation for a more complex layout or the legacy memory window. Once it is the new layout, so the new layout includes those attributes. It can include multiple layout entry types. We'll review them in a second, and also we'll have an example that will clarify things. So it can include an array of entries, and also the type. And the type is either composite or interleaved. If you recall from the earlier slides, a composite is merely taking multiple scatter-gather elements and combining them to one contiguous device virtual memory. And the interleaved is taking multiple areas and interleaving them one after the other. Explaining what is the bind layout entry. So we see this struct here. I'll review it quickly, but it will be more, it will be clearer in the example cases. So, that each entry, each layout entry starts with the object type, the sun object type, which memory key we are using. The memory key can be either a memory region, as described here, or a memory window. It can be already a pre-registered memory window. So this allows nesting of such a registration. We can have a memory region that describes a large memory, then we can define a memory window that allocates a portion or a window of that memory, or also that memory window can be of the non-contiguous type, where it can describe a composite or an interleaved memory window, and we can nest them. So this is the type here, and this is and here we put the corresponding memory region or window key. Then we mentioned what is the start address of the new memory window we would like to register, the length of each object, and then we can define if the memory areas that we would like to subscribe are composite or interleaved. In the case of the interleaving, there are multiple ways to describe them and multiple dimensions that we can support, and I'll show them in the next slide. So in a trivial case where we would like to, in this example for instance, we would like to register a block with length of say 4 bytes, and the stride is like 6 bytes, and we have 3 repeated scenarios of that block. So through using the bind layout entry, we will mention that the address, the offset for the first object would be 0, for example, saying this the first object resides in the main key in offset 0. The length would be the block length, the 4 bytes. And in the case of the stride would be 6, because that object is in that location in gaps of 6 bytes, and the count would be 3. So again, address is the offset, 0, length would be the length of the object, in our case 4. We have a single dimension here. The stride is 6, and the count, the how many objects we have here, is 3. Also, so this is the case how we use the bind layout entry to describe this pretty obvious object. The more complex fashion to use this layout is describing the cube or a portion of the cube, or a more complex repeating memory patterns where we have 3 elements from one area, 3 elements from another area, and 2 elements from another area, and we can repeat this 3 times. Again, those are use cases we've seen with real live application, and this is why we suggest to add such support in the API. To continue and describe how the example from the first slide where we did copies so far, how we deal with it here. So the example was how we take a column from a matrix. So in this case, we have a matrix, we have 8 rows and 8 columns. Each object in a row or column is of the size 8 bytes. So what would be the typical use case? First, simple, we create the memory window. It can be either registered by, the memory window is the one that describes the whole matrix. So it can be just a usual MR by using the good old IBV reg MR. It can be by allocating a memory window, the legacy memory window, and it can be by using the memory window EX. Once we have the Sun memory window, we use it now to register the column. And how we do that? We use the memory layout. We use a single entry in this case. We specify the Sun MR. That's the MR that was the output of the creation in step 1. Then we write the address. The address here, if we are registering the second column, it would be the offset from start here, so it would be 8. The length is 8 because each element here is of size 8. The repeat count and dimension count in this case is 1. Stride is 64. 64 is how many bytes we should jump till we reach the second object, which is the width of a line in the matrix. And count 8, we have 8 elements in each column. Once we initialize the bind layout entry structure, we are ready to call the bind memory window EX with the parent key, Sun key, depends how you look at it, and the bind information. And now we are ready to send the packet. We initialize a single scatter gather because now we have this memory look like this non-contiguous virtual memory look like a contiguous memory to the device. So we only need one single scatter gather for the device. We push the address, the length of this column. We use the L key of the created parent here. And we are ready to post send and send this column. So no need to do copies or to use huge scatter gather list, single scatter gather, 0 copy, and just send to the network. Another example is the interleaved case. So in the interleaved case, we use 2 entries. In each entry, we describe the matrix and then describe the column in the same fashion as we've done with the earlier example. We define the type here of the memory layout to be interleaved. So this defines that those entries would be, the objects of each entry would be interleaved. And we have 2 entries in this case. So we can see here that the output would be a contiguous memory of interleaved objects, one from the first matrix and the second one from the second matrix. Another example is the multi-dimension example. In this example, we can see that if we would like to take this 2-dimensional area from the cube, if we look at how this cube is built into the memory, so the first, if we describe the first column here, or a row here, it can be placed in the memory where each element on that first row or column is formed from another column by the length of the cube, which is n. So we need to jump n elements till we reach the next element in such a row. And once we need to jump to the second line here, we need to jump O double M elements because that's how the cube is placed in memory. So in this case, we need to use 2 dimensions and define that the stride for the first dimension is n, double the length of each object. In this case, we defined it as 3 bytes. So the first stride would be from that object to that object would be n times the size of the object, which is 3. We repeat that O times because that's the length of the row here. That's for the first dimension. The second dimension would be M times O times the size of the object. So this is how we jumped from this object here to the further object over here. And again, we repeat that n times because we have n elements in the z axis of the cube. Last example is how we can define a non-uniform patterns. The non-uniform patterns is that we can define a repetitive pattern where we take 3 elements from one entry, 3 elements from the second entry, and 2 elements from the third entry. So in this case, indeed, you are using 3 entries. The dimension would be 1 from each entry, but we can define that from each entry, we can define using the repeat count, which is a member of the entry layout, we can define how many elements are being taken from each entry per repetitive placement. So in this case, we take 3 from the red, we take 3 elements from the green, and only 2 from the blue as described on the bottom here. The count is the number of elements total that we take from each entry. In our case, it's 18 from the first 2 and only 12 from the third one. It's always a multiplier of the repeat count. And the stride can be different for each entry. In our case, we can see here that the stride is indeed different. So we try to show a more complex example where the memory patterns is not a uniform one. Okay, so to summarize what we've seen so far, using such hardware capabilities, we can have devices become more aware of the application objects, how their memory layout. Once it has this awareness, we can use this layout as a stencil and can define any objects using which are of the same type. Such an operation allows us to have an interesting non-contiguous virtual address space become contiguous for the device. So it's very easy to do network transactions, including RDMA, using such a pattern. The main benefits, obviously, is allowing us to do zero copy. We don't need to mess with the packing and unpacking. And also, we don't need to mess with the long scatter-gather list to describe the scattered memory. API-wise, we see that as a very good fit for the existing memory window that is already supported in verbs. Using the extensions that are suggested here, it seems like a natural fit. Thank you.
I have a question.
Yes, please.
So this is pretty, as a storage person, Tom Dalby, Microsoft, I'm pretty interested in this, especially when you consider persistent memory being exposed as storage across the network. It's a really interesting topology, if you will, of the memory registration. However, storage typically requires per I/O registration and deregistration. Memory windows have never been known for their high performance. They're good for, single long-lived registrations. That is the downside of reusing the memory window API. Can we get around that?
So I think that you would like to see that these operations are supported like the Ferrur operations, the fast register work request. So in order to perform
headline blocking, for instance,
Yeah, so in order to register such a memory, you send a work request and immediately can use that key in the following work request. So you can use that in the same semantics you use today for the storage.
Right. Yeah,
Also send with invalidate can be supported for such a key.
Yeah, most storage pre-allocates that stuff, though. we use FRWRs or FRMRs as the
Right.
language goes. So Windows behave a little differently from that.
So also with Windows Type 2, you can use a work request instead of a command to register such a memory. And if you do that on the same QP, and if it's a Type 2, you must do it on the same QP, so you can be assured that the memory window on the work request that was just posted, the memory key that was posted on a work request can be used on the following work request, which can be already a network transaction.
Yeah, okay.
So it should be pretty
so
efficient.
you're arguing that we'll get similar performance to an FRWR style workload?
Yes, of course there is an overhead. As I explained here, you can nest those memory windows. You can have one that is allocating a portion of another with this type of
the
patterns.
beauty of Windows. They overlay on an actual physical registration.
Yeah, exactly. So of course there is some overhead involved. If you use like a long nesting list and those objects are out of the device cache, then of course you need to pay a penalty. But other than that, the operation of registration and invalidation is the same as used today with the FRMR.
Well, assuming they perform well, which is, I guess, a big assumption, I would encourage you to think about storage-style workloads instead of purely matrix-oriented layouts.
Okay.
Storage workloads are typically page-based, but as we move to a persistent memory and a non-block-based back-end, I believe that will change radically. And I think this could be a good opportunity for an additional tool in the arsenal.
Interesting. Okay. And it seems like the composite type would be more of a match of such a memory layout if you have a different offset per page that we would like to describe.
As I say, it's a per I/O thing. So it's not like we have some sort of fixed geometry sitting there in memory. We've got some file, for instance, that was allocated in a whole mess of random regions of some DIM somewhere. We're going to open that file and map it, right? So we're going to have all these things laid out all over the place in not necessarily block-sized things. So this could allow us a very convenient way of mapping it. It could be dynamic. It could actually be long-lived as well if we're in so-called push mode, which is something I'm trying to drive.
If you have like a specific layouts that you would like us to examine, I would be happy to get them.
It's not so much a specific layout as a family of layouts. Right, you might have a metadata block, you might have a data block, things like that. And the inode is nothing like a data block, for instance. Okay,
so if you have such a pattern of layout that you would like us to look at, that would be interesting.
Okay.
So I can touch base with you and see if we can get in.
Thanks.
Welcome.
Yeah, in the storage context, I think that one use case could be remote scatter capabilities. So right now, you have scatter gather support on the local end, but you don't have scatter support on the remote end. Yeah, so this is a perfect match. One of the modes was called composite mode, which essentially you can put arbitrary scatter gather lists and then have a single key to address them.